presenters co-hosts. So just in case anybody has any slides to share, feel free. Fabulous. All right. So we're going to actually get started with a brief presentation from Spectrum. We got a couple of basic questions off of our questionnaire. So we're going to see if we can answer some of them with faculty input, and then we can go into the faculty presentations. So happy Wednesday, everybody, and happy Veterans Day. Thank you to all the veterans active and retired and Mason. So today our lunch talk topic is from stars to quarks, and we're going to cover different research opportunities that's available within the department. So the schedule for our talk today, if the slide will change.
I think I'm doing it.
Are you doing it?
Yeah. I'm on the schedule slide right now.
Oh, well.
Do you not see it?
No, I don't, but I will.
Oh, here, I got it.
What you're saying.
Oh, that's why. Sorry, guys, I don't know how Google works. There we go.
All right. There we go. So like I said, we're going to have a brief Spectrum introduction about how to get into research, followed by our faculty presentations. Professor Vora is going to be coming in later today. He has a standing appointment before this, so he'll be on at around 12:30. And then we're going to have a brief Q&A session. All right. So when should you start thinking about research? So that actually depends more on the field, but it is one of the first questions that people tend to ask when they get into university. So if you have a strong background in math or coding, or perhaps an intro to physics class, that's kind of your signal that maybe you can start to get into research a little bit more once you have a little bit of basics. But research really is just the icing on the cake. You have to put your grades in your classes first. Those can't suffer for the sake of research. So always make sure that you're not biting off more than you can chew, especially with STEM fields and STEM degrees. It can be very difficult to manage everything at once. And different projects require different levels of background information. And we can get into more personal experiences with that later on. So as far as doing research at George Mason goes, our professors tend to look for a student that has willingness to ask questions, a couple of basic coding skills, or at least a willingness to learn. To speak personally, when I started my research journey, I actually had zero coding experience. And it was a steep learning curve, but as long as you're willing to put in the time, most professors are willing to give you the opportunity to learn. They also want you to have good communication skills and responsiveness, especially to emails, particularly now with everything being online. They can't very easily check in with you personally, so they need to know where you're at, and you need to have constant communication. You also need to be able to work in a team. Most projects are part of a research group, and generally they're not individual projects. You are working with one other or several other people on the same thing, so you need to be able to communicate effectively with your group to move forward in your research project. You also might need to get assistance from multiple people, including the research students that are above you, like graduate students, and you need to be able to know how to work with them and how to accept their help. So you also need to be self-motivated and responsible. And I know that kind of sounds a little bit obvious, but it's very easy to sign yourself up for way more than you are able to take on. So every person gets kind of into this rut, or sometimes they can't get the work done. It's really important to be able to introspectively look at yourself and say, okay, is this rut something that I can motivate myself out of, or is this something where I need to take a step back? And taking responsibility for what you need in the timelines that you need them done is very important, which also just ties right back to that communication point. So as far as research topics that are available at George Mason, we have a very broad variety of research topics. We have a large astrophysics department, and while our astrophysics faculty was not able to present today, We do have research groups working in exoplanets with Dr. Peter Cloutchan and planetary sciences with Mike Summers, supermassive black hole and galaxies, like that's being done by Professor Satyapal and Professor Mario Guzzoli, and stellar astrophysics, excuse me, by Professor Zhang. So we also have material science and condensed matter, and those are being presented to you later. So I will abstain from saying anything there. In heliophysics and space weather, we also have Professor Zhang, Professor Weigel, and Professor Yeat. In STEM education, we have Professor Rosenberg, computational fluid dynamics, the Crash Test Center, and Professor Yang. There are also lots of external sources of collaboration that we have through our professors, such as at NASA Goddard, the US Naval Observatory, the Naval Research Lab, or NIST. So there are also possibilities for research there, either through an RU or through a professor in the department. So what should you be looking for in a research group? You need to know what your time commitment availability is and what time commitment is required of you by that research group. Do you want a project that can be completed in a semester or a year, or do you have several years to invest in it? That can help choose your research group. And we have several questions listed up here, like what fields are you interested in? What kind of skills do you want to gain? What are your skills now? Time commitment, like I mentioned before, large group or individual, lab, simulations, statistical studies. You don't need to know the answers to these questions right now, but these are the questions that you need to be thinking about when you start to choose a research group and a path forward in research. As far as how you find a research group, if there is a professor that you're very interested in their research, be engaged in their class if you're able to take a class with them. Visit office hours for help, do further discussions. Make sure you try to do well on their assignments and ask questions. Try and form a personal connection there so that you can more easily ask to do research as a part of their group. You also want to talk to other students that have worked with them to get a feel of if you'd like to work with them. Sometimes their teaching style does not collaborate with the way that they are an advisor for research. So you want to make sure that the way that they advise is something that works with you in your learning capacity. You also need to take stock if there's any skills that you need to brush up on. If you need to maybe take an introductory course in coding, or maybe look at Khan Academy, for instance. And the biggest, most important thing is to talk to the professor. Ask them about what projects they have going on, what they might have available for you. It's very easy to psych yourself out of talking to a professor, and it might even end up that they don't have availability for a student at that time. So make sure you talk to them and see what's available and what they are looking for as well. So when talking to the professor, don't think of it like an audition or an interview. It's just a conversation. You're just telling them why you want to work with them, what skills you have, what skills they need you to have. If what you're interested in lines up with what they're working on, what are your career goals and how can they help you get there, and how much time you have to commit to this. Research is two-sided. It's not just the student working for a professor. The professor is also working for the student and helping them along as well. So for anything that you do for the professor, you can expect it back in terms of, for instance, recommendation letters, or helping you make connections to people in other places, helping you get a job. You should get as much out of the partnership as they get from your research. And that is very important. So with that, we can move on to the faculty presentations, starting with Professor Sauer. And as I said before, if any faculty would like to comment on some of the questions that were addressed in this presentation, we welcome any additional guidance that you have. And we also will have a brief Q&A session at the end if anybody has any questions later. All right, so Professor Sauer, I turn it over to you.
Thank you very much. See, first of all, does everybody see a picture? Oh,
Yep, we see it.
Yes.
oh, wonderful. Okay,
But
great.
it's not the right picture. We see your presentation.
Yeah, I want to
like,
see.
not presentation. We see your presenter mode.
Oh, okay. Thanks,
You
Igor.
need to flip screens.
Flip. How about now? No, it's still presenter mode.
It's still presenter mode.
Doggone it. Okay.
You might have to select a different like window to share if Zoom gives you the option to do that.
Okay. Anybody know how to do that part? I could maybe share the screen.
I definitely did that before, but I don't remember the sequence.
You didn't remember the sequence of
Maybe-
it where you got there, huh?
Yeah.
Okay. Well, I'll see if I can share the screen. How about that? No, still same problem.
No, now it's
Now
fine.
we just
It
see your
looks good.
PowerPoint.
Now
Yep.
it's
There it is,
actually
yeah.
good.
Now it's actually good. Oh, okay, great. I can't see anybody, but please go ahead and interrupt me. So this is my group as of the spring. The ones that are in black, that's actually a Zoom meeting. So we had to go online. So we had a weekly Zoom meeting. And that's the members of the group. Now, Ben and Darwin just also started this past fall. Actually, Daniel's not working with me this fall, but was in the summer. So that's what the group looks like. And we study atomic magnetometers. We're interested in using light and atoms to detect magnetic fields. In addition, we're interested in doing something called low field or zero field nuclear magnetic resonance. That's where you can find the quantum resonances in materials, and that's due to their intrinsic fields. So you can do that for checkpoint applications, or you can do that for materials exploration. We're funded by the Army, by the National Science Foundation, and by QSEC, that's the Quantum Science and Engineering Center here at Mason. Now, we have a collaboration with Princeton and with a company called Twin Leaf. And the basic idea is that we use atoms, and the atoms have some resonances within them. We use alkali atoms, and you take light and you circularly polarize a light, you give it angular momentum, and you can then transfer that angular momentum to the atoms. And once you transfer the angular momentum to the atoms, they're highly polarized. And this is sort of showing you some of the structure. Guys, can you see my mouse? Can you see a mouse?
I don't see a mouse.
You don't see
no.
a mouse. Okay. All right. Well, we'll keep going.
Well, if you can go to your presenter screen, and then
yes.
you have several options, including mouse.
Maybe a laser pointer? How about that?
Yeah, yeah, that's good now.
Yeah, we can see that.
Thank you. Appreciate
Perfect.
that. Wonderful. Okay, so it turns out that what we are actually measuring is called the Zeeman splitting. That's what we use to detect the magnetic field. The magnetic field is when it's exactly the right energy to bridge two of these, then we get a nice signal from it. So we use these Zeeman resonances to measure it. So here, this is actually from our collaborators. They're building us two cells. These have the alkali atoms. They put a probe light. The probe light comes back and forth, and we're going to see the signal from that. And then we've got another collaborator, Twin Leaf, who's supplying the magnetic fields for us, and that's what actually does the tuning. So it does the splitting in those different Zeeman split levels. Now, the people who are working on this project are David Prescott. He's a research professor, and he's doing a lot of the optical work and the integration with that. And then Ben is doing the work with the magnetic fields, where the idea is that the magnetic fields do the tuning, and they're going to tune over two different frequencies. And for the people who are funding, which was the armies, those two different frequencies correspond to two different explosives. And so he's taking those measurements, as well as he's going to do some pulse sequence design and trying to make the two frequencies using a spectrometer. So those are their two projects. And this is just to give you a feeling a little bit for the lab. This is David Prescott again, and he's sitting next to his optics bench. And the whole experiment is an mu metal shield to get rid of the fields and thus be able to measure the sensitivity of things by themselves. So that's sort of the atoms and lights measurement of the magnetic field. The intrinsic resonances are really come from the fact that the nucleus has an electric, not always, but many of them have an electric quadrupole moment, so they're not round. And if you put that in electric field gradient, then you get quantized energy levels depending on the orientation of that electric quadrupole moment. And you can sort of put in radio frequency pulses that exactly have the right energy between the two the transitions, and you can get out. So what's interesting is that these materials, they have these quantum resonances, they're sitting on the table, they have these resonances all by themselves, you don't supply anything to do it. So you can basically put it in a resonant pulse and get out a resonant signal instead. So people who are interested in that, the interest is on checkpoint applications. And so I have Garrett Lee or Jake Lee. He's done some work on ammonium nitrate, and ammonium nitrate is a bucket. Ammonium nitrate, you might remember, is the explosive used in Beirut. It wasn't used, it actually exploded. It was being held there. So it's one of these fertilizer bombs. And so the military is interested in finding it. And so he's been able to do the first unshielded, meaning not in any shield. You can see that this unshielded detection of ammonium nitrate using atomic magnetometers. So that was just basically a couple of weeks ago. Along the same lines, you've seen Kyle, he's been hard at work. And he's done the first detection of 39 potassium and potassium chlorate via conventional NQR. So that's the nuclear quadrupole resonance I was just talking to you about. So the kind of work that he works on is building a probe like this. It's got inductors and capacitors, and he has to figure out different things about the inductors and capacitors to make it resonate with the frequency of interest. Right now, the huge tube that you see him playing with is actually a temperature control, because it turns out that this particular signal has a pretty high frequency coefficient. And so that's what he's doing at the right then, because as soon as he can lock in the temperature, we can measure all kinds of relaxation constants, which will help us with the measurements. Darwin, who just came to our group in this fall, he's been working on something that combines ammonium nitrate and potassium chlorate. So he's actually built a coil. You can see it here. It's got the 2 bottles in it, and he's designed the circuit to be able to have this coil actually resonate at 2 frequencies. So we can do the detection of both ammonium nitrate and potassium chlorate. So another aspect of the project is with doing some theoretical studies, and that's what Professor Mazin, and he can probably tell you more about it than I can really. But the idea is that we'd like to be able to detect the quantum resonances, not just for checkpoint applications, but also for materials exploration. And this is actually from work done with Kamal Chowdhury at NIST, in which he looked and he found electric field gradient, so that determines the frequencies of many of the nuclei that are in the periodic table. And so that's this picture over here to the left. And so I'm not going to discuss too much about those theoretical calculations. Igor, I thought you were talking, but I think you're not talking, are you? No,
I actually am talking, but
you are giving a presentation,
but not about this particular part. But
okay, all right. Well, anyway, you'll get to meet him and hear about him. But really, it's Professor Mazin that knows about the density functional theories. And so through the density functional theory, the idea is to calculate electric field gradients in materials that haven't been studied before, and also internal magnetic field gradients. So the chief person on that has been Jafar Ansari. Jafar, I think you're on the call maybe. Anyway, you can contact Jafar and ask him more about that project. Finally, one of the other projects, a lot of them are related, you can see, is not just to find these new resonances theoretically, but to find them experimentally as well. And so you can see here, this is Daniel. Daniel is at the end of the summer, so socially distanced, has his mask on, and he has worked very hard at trying to make coils that can actually have a low field outside while having a really high field inside. So you can think about the infinite solenoid plus. And so the plus part is he's making coils here at the end, and we've gotten good success, basically a reduction from the inside of 5 orders of magnitude, and we're hoping for a 6 order of magnitude. Robert, right now, I think even as we speak, this guy over here, he's a graduate student, he's working to get that down by another order of magnitude. We did work on actually not just trying to do this correction coils, as Daniel did here, but we also tried to do 3D printing. In fact, Jafar did that part as well, this 3D printing part, where we actually made the spacings to be such that the field outside should be very small. It turns out that some limitations in 3D printing sort of limited us. So overall, what are we about? We're about atoms, light, quantum resonances. What are the skill sets you need? Quantum physics, electricity and magnetism, electronics, kinds of things that you do. You play with optics. You maybe do some 3D printing. You do some electronics. You can do some modeling. The density functional theory has to be done in collaboration with Professor Mazin, so you have to talk to him about that. And that's about all I have for you today. I'm happy to have your questions.
Great. Thank you so much, Professor Sauer. Does anyone have any specific questions for Professor Sauer and her work? She can also be contacted through her Mason Live email. Okay. Then I think with that, we can actually go on to the next presentation. So Professor Mazin or Professor Ghimire, whoever wants to share their screen, if you need to, but the floor is yours.
I will. So we agreed that I will present our joint presentation. Let me get it up and do proper sharing. All right, so let's see. Give me a second. Share screen, and I believe it should be screen 2. So can you see my screen now?
Yes, we can see it.
You can see it. Now let me now do this trick with the pointer. So that would be laser pointer, and that should be here now, right? Okay. So this is a subset of what Nirmal and I, and my name is Igor Mazin, this is Nirmal Ghimire. We have very different backgrounds. He's experimentalist, I'm a theorist. And we decided to present, as I said, a subset of what he's doing. He's doing various things, and I'm doing various things. Among them, particular collaboration with Karen on NQR, but that's a different story. But we also work on what could be called quantum magnetic materials. I will explain in a moment why do we call them that. And that's very intertwined work of experiment and theory. You may have noticed they are more, we are condensed matter or condensed matter slash material science group here is a rather tightly bound. We collaborate a lot among ourselves. You will also hear from Patrick Vora. There are quite a few other people. There are a couple of theorists as well. For pure theoretical physics, it's a bit challenging to fully engage an undergraduate student because of much of knowledge that you need to have before. But it's not a bad idea to start. I myself started when I was a junior in college, working with an experimental group, doing some minimal experiment and also doing some literature research for them, but getting to understand how the measurements are being done, how the experimental data are being processed, and also gradually getting myself into theoretical physics. So we, after several discussions, we decided not to go into detailed presentation of specific measurements or specific calculations as Karen did. There's nothing wrong with that, but we thought that maybe it would be better to spend our 15 minutes of fame on to sort of conceptual discussion. And whoever is interested and wants to know more about this the technical details of what we are doing, or even not so technical, that of course both Nirmal and I will be happy to talk to you. So first of all, what are quantum materials? I mean, this is the wording which is floating around a lot. And what also several quotations. One of them is materials in which extraordinary effects of quantum mechanics give rise to exotic, often incredible properties. Doesn't really tell much, but that essentially quantum materials are materials where something that happens at a microscopic scale on a scale of individual electron affect in qualitative and important way the macroscopic materials properties. In particular, magnetism is a very good example of a quantum material. You see, you can, depending on whether you have taken quantum mechanics or not, you may or may not know that each electron has a property called spin. So it's not only a small minuscule charge, it's also a small minuscule magnet. Now, in the material which does not exhibit magnetic properties, like a piece of aluminum, for instance, all these microscopic magnets are completely disordered, and in fact they also dynamically disordered, so they change their orientation all the time. In magnetically ordered materials, these magnets are all proceed in a coherent, ordered way. So it's like a crowd or a marching band. And they can be ordered in many different ways. This is the simplest possible. And sometimes the way how they are ordered is very complicated, and it's not entirely obvious, and you need a joint effort of experiment and theory to understand how they behave with respect to each other on the microscopic scale. That's arguably the most common and the most dramatic manifestation of quantum cooperative effects. So why it is quantum? Because each of these little objects is completely quantum object, controlled by quantum mechanics, Schrödinger cat, whatever you have heard about quantum mechanics. At the same time, all these objects behave in correlated way, so it's a cooperative effect. And this correlation is macroscopic. It's going across one part of a piece of material to the other. And there are actually relatively few effects which sort of span atomic and macroscopic scale with the macroscopic human scale in such a coherent way. And as you know, there's magnetic materials occur in our life everywhere, and also in a way which we don't see, like for instance, computer memory is mostly magnetic now. There's a lot of computational power that can be derived from microscopic magnetism. Quantum computing that you may have heard about may relate on complicated and non-trivial magnetic properties and so on. So that's idea of why we're studying them, besides that they're very interesting themselves. So why do we have a quest of new quantum materials? And as I say, that all comes, to be honest with you, not everything that we are doing has immediate application, can tomorrow appear on shelves, even though that's a distant goal. The science work in a way that in some sense we are trying to satisfy our curiosity. We try to find something interesting, some uncover internal beauty in the laws of nature. But the world is organized in such a way that the more you know about this world, even though at some moment it may seem completely irrelevant for everyday life, eventually it finds its way into daily life, and it's like a pyramid. If you want to talk, this pyramid is something like a modern computer, but at the bottom is a very big foundation of very general knowledge, which probably would never be there unless people were just curious to find something interesting. But anyway, going of materials, we see that historians sort of break our time on Earth into epochs or eras, which are characterized mainly by materials they had been in use. You know, Stone Age, Bronze Age. We are now living in Silicon Age, but it's generally expected that we might be on the borderline of another breakthrough, which would be based on newer and more exotic material properties than just pure silicon transistor. And that's actually already, we are somewhere here because that's already appearing. And part of this new material foundation will be our quantum magnetic materials. So to go, so we study materials, and as I say, we don't necessarily study something that can be made into a working working gadget tomorrow, but we are studying materials which are interesting and unusual and hadn't been studying before. And the concept, general concept, what we are doing, and that's what we are trying to implement in our shall we say this joint project with Nirmal group, is combining several different aspects of scientific work together. One thing when you study new material is to be able to actually synthesize these new materials. But another aspect which comes very often into the game now is to be able to actually predict new materials theoretically. I will not go into detail. In the last several decades, there have been a lot of progress on, as people say in Latin, in silico, making materials inside the computer in a way, studying their properties. And this theory, quantitative theory, which was good part of it is referred as density functional theory for the reasons which are not relevant now. That's what Karen was alluding to. These are possibilities, and one of the most interesting, again, you may have heard in headline news that recently something called room temperature superconductivity was achieved, which was a holy grail of many condensed matter physicists for a long time. Unfortunately, in the moment, it's not practically applicable because it only appears at super high pressures in a very small samples. But the interesting part of that, these materials which are touted now, they had been predicted before in an entirely computational way. So another thing is that after we have synthesized a new material, we characterize that, and we, in this case, means Nirmal and his group, by measuring variety of physical properties, magnetic properties, transport properties. And when we say transport, that means that how this material transfers electricity, heat, and how these transport properties are affected by external stimuli like external magnetic field, temperature, and so on. Then we do specific experiment on that, and then we try to understand this experiment, and here the theory comes again. So basically, theory is trying to relate whatever is measured by these devices with whatever is happening quantum mechanically on the microscopic scale with individual electrons. After you have worked there for a while, you might get familiar with funny conversations among theorists. No, electron doesn't want to live in this quantum state. No, it's not a good state. It wants to live elsewhere. In fact, in languages which have grammatic genders like French or German or Russian, that sounds even funny because it's, oh no, electrons, no, he doesn't want to sit here. It wants to sit elsewhere in another quantum state. So anyway, so basically that is, we are speaking about making materials, measuring materials, understanding materials, and improving materials. And ideally, all this part of this process, it's a circular process. It's not a linear thing because you can at any point you can jump to any other point and back. That's a conceptual part of what we are, of how we do our studies. So specifically, as I say, synthesis is something that Nirmal is an expert in, and he can tell you more about how it's technically being done. I believe that there are some parts of this lab work which can actually be done under guidance by undergraduate students. I know that Nirmal worked with an undergraduate student very successfully in last year. So there is a essentially growing a crystal, something you may have done even at school, growing salt crystals from solution, but there are more sophisticated methods for that. And these are some examples of materials that he had grown. Some of them are chemically simple, some of them are chemically extremely complicated. All of them have quite unusual arrangement of atoms and magnetic moments. All of them are interesting magnetic materials. These are a couple of things that he's, and in fact, we've been collaborating on some of these materials, trying to understand them also theoretically. So then there are measurements, and again, there are many ways to do these measurements, and in good scientist tries to measure not just what he or she has handy in their lab, but whatever the anticipated physics requires. So one thing which is not good is searching for your car keys under a street light. You know that story about a drunk who is looking for his car keys under street light, and why? Because there's light there, not where he lost them. So some of these things can be measured at home here in Nirmal's lab. For some of them, we need to go to our collaborators at other places. This particular neutron diffraction is being done because we don't have our own reactor at NIST. We also collaborate with many other institutions, both Nirmal and I, across the globe. I have collaborators in Japan, in Europe, in Russia, in India, in Nepal. We are collaborating now with a fellow in Nepal on doing calculations for one of these materials. So that's how they think is working. So we are trying to get consistent picture of everything which is relevant for this new material. So the theory is done in two different ways. There's computational theory, and that's essentially trying to, again, if you have taken quantum mechanics, you know that at the end of the day, all quantum mechanics is described by Schrödinger equation and Dirac equations. The problem is solving these equations for something like 10 to the power of 23 electrons. There are methods for doing that, and there are methods for extracting some interesting and measurable information from that. That's done on big computers. We have some small computer cluster, microcluster. Again, in my group, there is computer cluster much larger at the university, and we have also access to supercomputers as the Department of Energy and Department of Defense. That's one part. Another part is analytical calculations, which is very large. Basically, computers is stupid. It gives you numbers, but to analyze these numbers and to understate them usually takes much more time and much more mental effort. That's something which is probably difficult to get engaged right away, because for that you really need to know a lot, to know quantum mechanics, to the electricity and magnetism, statistical physics, and many other things. But eventually you get there. You never stop learning. I'm 65 and I'm still learning new methods and new theoretical techniques. But that's an indispensable part, and there are some other theorists in our group which actually do not work much with computers, but mostly with analytical. Now, I'm saying analytical, but it's not necessarily always a blackboard covered with formulas. More often than not, modern theorists use such tools as Maple, MATLAB, Mathematica, and it's an important part, and that's something that you can learn while working on an actual project of how to use these mathematical packages to simplify analytical calculations. All right. So what do you need to? Was partially covered in Natasha's introduction, but she was absolutely right. You definitely need to be responsible, careful, and well organized. Because if you have taken classes and you know how often you fully understand the problem, then you go through that, and at some point you forget about factor of 2, or inadvertently change a sign, and then your final result is completely wrong. So you have to be careful, you have to be well organized, and definitely if you work with other people particularly, you have to be responsible, because you are it's a project often involves several people, sometimes a dozen of people, and they all need, for different reasons, to have their research published, presented. And if part of this research is on your shoulder, that you have to be responsible in delivering, or saying that you cannot deliver. Now, whether you are experimentalist or theorist, you need to be good with math. You need to understand math, particularly if you're experimentalist, you need to understand very well the mathematical statistical methods for processing your experimental results. That you definitely need to take classes in quantum mechanics and solid state physics, and in principle, E&M for sure, and statistical physics. And most of all, you need to be interested, engaged, inquisitive, imaginative, interested and persistent. And the worst thing that can happen with physicists is lack of imagination. Anyway, so as all right, now a little bit about what we're doing. So Nirmal still insisted to on including some of the actual measurements, so you wouldn't know what the Hall effect is. Let's say that some way how electric current can be influenced by magnetic field, which is not usual. And that's a very intriguing observation that we are trying to explain now. It's not easy. Here is the, I don't know why he rotated it this funny way, but that's the more straightforward is how magnetic moment of your sample depends on magnetic field. But again, there are very interesting things going there as a function of temperature, and we are trying to understand that. One graduate student working on that is Connor. There are more people working with us, so that's a little bit about ourselves. So we are in different age group, but we are share interest in solid state physics. I'm a theorist. I used to work for the Navy for many years, for 20 years, and I just joined GMU last year. And Nirmal experimentalist, and he started his career as a professor 2 years ago. Already has made a large imprint on in our group, and we work with several junior colleagues. In particular, as you see, the Nirmal group is very diverse, and that reflects the fact that in experimental lab you can find occupations for people, easier to find occupation of people in different level of education. So that's it. And as I say, I avoided nearly entirely any sort of specifics of what we are doing. But if you are interested in that and want to chat, that both Nirmal and I will be happy to talk to you. Thank you.
Wonderful. Thank you so much, professors. That was great. I know that Professor Vora has a hard stop time, so maybe what we can do is we can do his presentation and then we can have cumulative questions at the end. So Professor Vora, the floor is yours.
We are unmuted. There we go, and we're doing it live. All right. Thank you, Natasha. I appreciate it, and thank you, Igor, for covering awesome ground on this, making it so I don't have to do quite as much background here. So I'm going to just bounce through this as quick as we can. Lickety split. So, you know, first and foremost, thank you all for coming today. We really appreciate. I really appreciate you being willing to learn more about, you know, participating in research here at Mason. We need good, smart, young people who have energy to, you know, actually do the stuff we're too old and slow to do, right? So I want to just tell you a little bit about my group first, and then I'll try to motivate for you. And it may retread a little bit of the ground that Igor's covered here, but I'll try to motivate for you a little bit why we care so much about materials and the scope of fascinating things you could do there. So this slide is actually a little bit dated. Some of you may know Jack Goggin, Cicely Matete, and Adam Robinson, who have replaced these guys as our undergraduates. But my two graduate students, one of them has graduated and he's now got a full-time job at MITRE. Jay is finishing up, will graduate in May. Iris was an undergraduate and a simply force of nature. And she went from political science to physics, and now she's doing a neuroscience PhD at Princeton. And Sam Yee was in our group, and he's now at Raytheon. He did a lot of work on the zirconium system. So, and in addition to the wonderful students, excuse me, Juniper, quiet. In addition to the wonderful people that I've worked with here at Mason, we've collaborated with a lot of other people at Penn State, Miss Gaitherberg, UVA. This is by no means a complete list. So that's just some idea of it, but we are linked quite closely with Albert Davidov and Sergei Krylyuk and NIST, who've grown a lot of the materials that we've interrogated. Now we're funded in the past by ONR, by the National Science Foundation through an Igor Award and a Career Award, as well as funded by the GMU QMC, which has now been relabeled as the QSEC, so you can tell these slides are a little dated, and also by the Materials Innovation Platform at Penn State, from where we get very interesting and exclusive materials that we like to study. Okay, so that's the broad overview. And just an idea of some of the sorts of things that we work on. So you've heard a bit about, materials earlier from Igor. We're very interested in 2D materials as well as their heterostructure. So the image you're seeing here was actually created by a Mason undergraduate, where she went ahead and created a sandwich where she put a layer of HBN, then put an atomically thin semiconductor on top of the HBN, and that's, can you see my little laser thing here? There we are, atomically thin semiconductor in there, and then capped it all off. So you've got this sandwich that you probably wouldn't want to eat, but actually leads to very interesting physical phenomena. And so we've published a lot on that topic in reasonable journals. We occasionally do stuff with biophotonics. So colleagues at NRL have given us DNA that actually has little quantum emitters on there that they can control the coupling of, because they can control the configuration of the DNA and the geometry in which it assembles. So that allows us to explore energy transfer between these quantum emitters on a DNA backbone, which I think is cool and weird. Okay, what else? We do look at quantum devices as well. We've done electronic transport and magnetotransport down to cryogenic temperatures. And my past work, I've done some quantum optics where I embed quantum dots in photonic nanocavities. Animations are semi-functional here, but a lot of what we've looked at are 2D material alloys, and they are potentially very useful for technology. So I'm going to talk a little bit about the need for that kind of materials research and where the state of the art is on the subsequent slides. But I do want to highlight some of our new projects. One suffered from an extra copy and paste, but that's okay. We've launched a new effort in our group for machine learning identification of atomically thin materials. And so this makes it very easy for us to identify and determine the layer number of a wide range of these 2D materials, which are just a few atoms vertically, but extend as far as you like in the 2D plane. We've been fortunate enough to get some new instrumentation this year. So we will be bringing online a new magneto-optical cryostat, which is going to be able to let us get down to 2 Kelvin, so colder than the background of space, right? Colder than the cosmic background, and magnetic fields up to 7 Tesla. We are also bringing online a supercontinuum optical source, which is ultra fast. It can send out short picosecond pulses of light, and bringing online a second harmonic generation system, which is actually really cool. You send 2 photons in at one wavelength, and you get a new higher energy photon out. So it's very useful for studying crystals. But why care about this stuff in the first place? Well, one area which is important and demands material solutions is computing. So there's this study that was done by the Semiconductor Research Corporation and SIA, funded by the NSF, so many acronyms, so much time, which attempted to extrapolate, how much energy is presently consumed by all the computers on the planet, and based on the present uptake, increase in usage worldwide, where are we going to be in the future? So where we are right now is the orange line. That's where we are, and that tells you how much energy you need to flip a bit. And the yellow line, you can barely see it, but it is sloping upwards very little bit here, and that's the anticipated world energy production. And so what you can see is that if we don't make our computers better, we're not going to be able to keep up with the energy that they need. And so that alone makes a sustainability challenge. So here's a way to understand it a little bit better. I hope everyone's seeing the GIF, right? There's this famous song you may have heard. I like the GIF, it's fun. I had to clip it very selectively to make sure it was safe for public use. This song, Despacito, right? It is by the great artist Daddy Yankee. And this song is very popular. It's had 6.6 billion views the last time I checked on YouTube in 2 years. That's crazy. We're approaching the population of the planet. That's nuts. So what does that mean though, in terms of the energy to view it? Well, this wonderful song costs a lot of energy to view this many billion times, right? And every jewel is worth it because it's a great song. But here's an idea of the scope here, right? So one estimation by this lead scientist, Rahul Bash, I can't say it, I won't try, has basically shown that this song being played this many times, and at the time it was 5 billion, I think, is cost more energy than 5 countries, African countries use in a single year. That's crazy, right? To me, that's crazy. Another estimate also kind of drives home to you how much energy we use here in the US. This amount of energy of this group of 5 countries is equivalent to just 40,000 US homes in a year. So this is a huge amount of energy that goes into just playing this song. And when you imagine scaling that up to the internet, right, to all the things that we do, and also local computing tasks, I think the idea becomes quite clear. Now, how am I doing for time? Probably terrible. Oh, I got a solid 8 minutes. Yeah. So that's not the only challenge that computing poses for us, right? We are reaching performance limits. You can only make transistors so small, and you can only pack them so tightly before the heating of each individual transistor, before it becomes very difficult to get the heat out. Think of it as having like a bunch of little wires, and you're putting them closer and closer and closer together, and you're trying to extract the heat from the system, but that's very, very difficult the tighter they're packed in there. Right. So there's been some progress on that, but with creating vertically integrated transistors. But there's a fundamental bottleneck here. And what that is the inherent architecture of our present computing systems. And this is called the von Neumann bottleneck. And basically, every time you do a computation, you go and you fetch the thing. Let's say you want to add 1 and 1. You go fetch 1 and 1 from your memory. You bring it to the CPU. You add 1 and 1, you get 2, and you send that back to your memory, and you're ready to do the next computation after that. Now, that all sounds well and good, except you're sending this along physical wires between these 2 units. They're spatially separated, and every time an electron moves along a wire, you generate heat. So there's a huge amount of waste heat from this process. And in addition to it, the operational speed of the computer isn't so much limited by the CPU or the memory as it is by the interconnects linking these 2 units together. So there are fundamental problems with these that limit both their energy efficiency, which is a clear challenge for us as a society, as a species rather, and also in performance, where you're being limited by the way we build computers here. So there are a lot of ways. Okay, so moving forward, there are ways that you can get around this. You can address both the energy and the performance challenges using a bunch of new computing technologies. One is spintronics, and this is very relevant to what Igor and Nirmal are working on. So in this sort of thing, you are using spins, electron spins to do your computing, and you're able to move the magnetism, but the charge can stay put. So you're able to separate a spin current from a charge current. Now, if you want to imagine this in terms of anybody seeing the Nationals, right? You get into a baseball game, right? And you do the wave. I don't know if you're able to see me in the thing, right? But you have thousands of people, right? In this thing, right? And so pretend the arms are your spin information. So this is spin up and this is spin down, right? And so when I do the wave, right? The information of me going into spin up propagates around the stadium, right? But I didn't move, I stayed put. So the charge stayed put, but the state information moved. So this is great. You aren't moving charge, no more RC time constants, right? You aren't moving charge, not as much heat generated during a computation, a lot of wins. Another option is optical computing, where you're moving light around. It's a lot faster, less energy intensive, and it naturally integrates with our existing telecom networks, which is wonderful. This is my favorite, neuromorphic computing, where you're building a hardware analog of the brain, which is kind of crazy, but also freaking cool. So here you're constructing artificial synapses made of material components that are able to alter their phase. And upon repeated flipping between 2 different phases, you need less energy to flip it. So the hardware learns, not the software. The hardware of the neuromorphic computer physically alters in response to stimuli, which I think is remarkable. And of course, there's quantum computing. Now, quantum computing offers us the performance boost. It doesn't offer us the energy help we need, but it does make it so that we can solve problems that are presently totally intractable. And that could be really powerful for solving a lot of the most important societal challenges that we face. Okay, so at the core of this, of course, I'm blowing through my time. Maybe I'll skip this, but what do we take? No, this is worth it. In quantum materials, right, why are we so excited about these things? And Igor gave a great description of it. I like to use a very stupid description, which involves birds, because I like birds. So this is a single bird, right? And so I want to explain, what emergent quantum phenomena are and how they can occur in quantum materials here. Okay, so quantum materials have properties that you can't explain using single particle physics. Okay, so let's replace single particle with single bird, right? A single bird likes to fly. It is good at flying. That is good. Now, single birds, they are small and easily eaten, right? So maybe they like to hang out with a lot of their friends, right? There's safety in numbers, and the probability of being eaten is lower when I'm hanging out with my friends than when I am moving by myself doing whatever I want. Now, I want to be near my friends. That's an attractive bird-bird interaction, okay? So that's attractive coupling between my birds. However, the birds wish to fly without crashing, right? So that is a bird-bird repulsion, right? They don't want to be too close to each other. So you have this balance of desire to be attracted and also a balance of the desire to have enough distance to safely fly. So what that can lead to in these large grouping of birds is behavior of the flock controlled by the birds on the edges, where a few of them will turn one way and all the rest will gradually stagger and follow in order to maintain the balance of being close to their friends, but not too close to compromise their flight paths. And so what you end up with is this beautiful flocking behavior where thousands of birds move as if they were one organism, but they're not. They're individual actors that follow simple rules for interacting with other individual actors. If you replace the birds with electrons, and you put them in a crystal lattice here, that's where you get a similar effect. This is what people mean when they say emergent phenomena. You have lots of electrons, you have lots of interactions between them, and the balance of those, all the interactions between them can lead to new, emergent, and completely unexpected behaviors. And one example I'm showing you here, this is this bar down here is 1 nanometer. So you're seeing actual atomic resolution of charge in a crystal. And you'll notice that it isn't uniform. This crystal is a metal, and so the charge should be just uniformly spaced every which way. But if you cool it down to a low enough temperature, the electrons bunch up and form a new superstructure with a new symmetry. And this is something called a charge density wave, and it's the basis of a lot of proposals for new memory technology. So this stuff is really cool. It's really useful potentially. And a lot of the times you're really going into the unknown. Some of the most interesting stuff we never expected to find. A lot of these things are very hard to predict from ab initio theory. So it's really cool. It's really exciting, and it's also really applicable to important challenges for our society. And that trifecta is what makes me so excited about working in this field. Okay. It's underneath the thing. Disaster. All right. I'll skip this. This is just showing you that these kinds of effective interactions can lead to electrons behaving as if they have no mass, but they do get to keep charge and spin. So there's this theoretical particle, a massless Dirac fermion, that's never existed, by itself in nature, but we can play with it effectively in a crystal. And that sort of thing continues in a bunch of different materials. All right, so superconductors, that's an emergent phenomena. Magnetic monopoles don't exist in nature, but if you get the right combination of atoms and electrons arranging in a certain way, you can create an effective magnetic monopole inside of a crystal, and you can play with it. So doesn't exist in the regular universe, but in our materials playground inside of a crystal, we kind of control the universe. And so we can make it so that monopoles exist. You can have these massless Dirac fermions, and you can also get wonky, weird stuff, such as topological insulators, where you can have dissipationless current along the edge of the crystals. And what do I mean by that? That it's completely insensitive to disorder at the edge of the crystals. It's almost kind of like a superconductor where it can move without really any resistance. And it's also a spin polarized current at the edge. So that might be super useful for spintronics in the future. Okay, am I out of time? Can I steal 2 minutes?
We're at
Sure.
1, and you're the one that has hard stop. So as long as you have.
I'm usually late to everything. 2 minutes. All right. So we like to explore layered quantum materials in my group, but we'll measure anything that you can put on a substrate and make cold. So why layered materials? Well, first of all, you've heard of graphene. Graphene's super cool. Everybody loves graphene, right? And that was the way, that's all it was for like 5 years. And then we discovered semiconductors that have this layered structure to them, in-plane covalent bonds, out-of-plane van der Waals bonds. So you could isolate one 3-atom thick layer of a semiconductor. It was great. People wanted that for graphene for a long time. Then we discovered, wow, look at this. There's charge density waves in superconductors that are just 3 atoms thick. And then we discovered, wow, there are topological semimetals that are just a few atoms thick as well. And then we're like, wow, they're magnets and they're just a few atoms thick as well. And so this opens new doors for us, right? And so, I think, okay, this is 4 or 5 examples, but there's this wonderful study in Nature Nano, which looked at a database of 200,000 crystals and found that out of the 200,000, there are 2,000 atomically thin compounds available, each with its own unique band gap or magnetism or electronic behavior or what have you. And this is cool because what we can do is we can make stacks on stacks on stacks on stacks on stacks now, right? So normally when you make a heterostructure, what that means is you're growing one crystal on top of another crystal. And to do that right, it's like having Legos that are it's like Legos. You need the periodicity between the hole patterns and the pegs to match. So when you have that, great, it fits well. But if the materials you're trying to grow on top of each other are radically different, they won't fit together, they won't mesh well, right? And so that is true when you have a crystal that's 3-dimensional and bonded covalently in all directions. But for us, it's only covalent in the plane. Out of the plane, it's very weakly electrostatically coupled. So unlike what we've been able to do in the past history of materials science and engineering, we now can put anything on anything. It doesn't matter. We don't care. We can get a monolayer of anything and stack it on anything else. And this is a fundamentally new capability. It points to a lot of really exciting and interesting physics at the interfaces of these two sorts of compounds that we've never been able to do this before. So it's very, very exciting. And then more propaganda follows, but that's enough of that. So thank you guys for the time and opportunity and for bearing with my verboseness and gesticulations. I think I may have pulled something in my shoulder.
Right, thank you so much, Professor Vora, and I think he's gonna dip out. Okay, so it is 1:03, but if anyone has any questions, feel free to stay on. We also have a couple of questions from the chat. There are 2 that we got most commonly, so we can just go over those very quickly if nobody has a hard stop somewhere. So the first big question that we got was, I'm really scared to ask my professor about research. What is the best way to ask a professor about joining their research? From the student perspective, I can understand that was kind of a terrifying moment. But really, you just kind of have to get someone to hype you up, to send that email, make sure it's professional, and then you just wait. But if any professors have something to say about the professor side of having a student ask about doing research with you, that would be great. You're muted.
I think
okay.
what you said is just right, Natasha. You just need to get over the barrier and know sometimes that opportunities just come at the right moment and sometimes they don't, depending on whether the funding's there or the time is there. So to not be shy and to spread your net wide. All the people that I know who are here at Mason as professors, they came to Mason, they came to the university to work with students. I mean, otherwise we'd be someplace else. So go ahead and write those emails and also spread your net wide and because the opportunities with professors come and go according to their time and also their funding.
Wonderful, thank you so much. And then the other big question that we got was, what type of coding languages do you usually work with?
Shall I answer that?
Sure.
Okay, so traditionally, there's a really big codes in computational physics, computational material science are written in Fortran. Now, this said, at some advanced stage, you may need to modify this code, but more often than not, you just need to understand how the code works. So there are input files which are often complicated, includes a lot of information. There are various regimes, various parameters. Much more important than knowing a particular programming language is to understand the physics of that goes into this programming. Now, the next part, and that's something that everybody has to do at some point, is processing your results, being experimental results or computational results. And to that end, essentially any language you like would go. In our young days, that was Fortran. Then many people switched to C, and now probably the most popular language is Python. As I mentioned, another tool which you can't call coding, but it's really it's not exactly what you usually understand under programming, is working with interactive computational systems like MATLAB or Mathematica. They have their own language, their own syntaxes, and my feeling is that, that this is a very useful skill. Not necessarily all of them, but know one of these packages good and understanding how to achieve things. That's it. And the third thing is visualization. Again, whether you're experimentalist or theorist, at some point you will want to see, to view your data in a visual form, and that involves not just plotting A as a function of B, but often you need to handle isosurfaces in three-dimensional space, or colored plot where this is like three-dimensional scatter points with another quantity encoding and coding in color and so on. So presenting your results well is important for yourself, and it's also important for selling your data in your talks and paper. So that's what I can say to that.
Excellent. Well, thank you so much. That was very informative. And if
And I can
anyone
talk-
else, oh,
I can
yes,
talk
go
from
ahead.
the Astro side. So everything that I've written and most things that happen in Shabita's group at least are either in Python or IDL. IDL being a lot of our data reduction packages, and then Python being pretty much everything else. But I've worked with a lot of different coding languages over the different projects that I've done. And once you learn one, they just become easier and easier to learn. So it's a matter of just changing which syntax you use. So the best one to start learning is really just whichever one you have the best access to, which Python has a ton of things online.
That is correct.
Yeah, and Khan Academy is great for a lot of this. Whatever, and then just kind of adapt the rules and that kind of way that you learn to think about coding to whatever language you ultimately end up using.
Yeah, one other important skill is knowing Linux system, because nearly all scientific computations are done on Linux and not under Windows or something like that. So that's another, and also to some extent knowing scientific text processing. So while particularly in experimental science, you often can get away with the with just Word, serious paper requiring lots of formula is usually written in LaTeX. So that's another thing which is useful.
Yes, that is very useful. And learning LaTeX certainly has a learning curve, but once you get over that hump, it tends to make a lot more sense. So thank you everyone for your time. If anyone has any other questions about getting more involved with, for instance, astrophysical research or other areas of research that's in our field, please feel free to contact Spectrum or your individual professors. Thank you so much to all of our speakers, and they are available through Mason Live as well if you are interested in joining their groups or learning more about their research. As always, we will send out the recording of this talk. And if anyone has any other questions or information, or you're looking for resources, please feel free to reach out to any one of the Spectrum leaderships or a trusted professor, and we can get you where you need to go. So unless there are any last minute questions, then I think we can call it a day. Again, thank you so much for attending, everybody, and thank you so much for the presentations. All right, fabulous. Bye, everybody.